Okay, so in the previous lecture, we had left off right here saying that we will be discussing the conservation of energy next. And I had said that we'd discuss a conservation energy for a control volume. Obviously, this is the final goal where we want to go. But before we discuss conservation of energy for a control volume, we should be discussing conservation of energy for a system. Okay. Okay, so now here what we want to basically do is that if you go back to the Reynolds transport theorem, the relevant parameter here, okay, so the relevant property B is total energy. Let's say we write it as E. Okay, and then we have to find out what is so we have to use d by dm, which will be beta for this particular case. But before we do that, now we want to understand what is the conservation of equation that we should be applying to a system. So now some of you may be doing the not the heat transfer, but the thermodynamics course right now, but many of you might not be. So I think it is only pertinent that we discuss this issue of the thermodynamic laws as relevant to this fluid mechanics class right here. So let's say we have a system, okay, which is again a closed set of closed mass system, and the first law of thermodynamics, okay, can be rewritten as so the first law of thermodynamics can be written as d being equal to dq plus dw. Okay, but here we have to be just a bit careful what dq and dw are. So now dw here is the work done into the system, and this is heat energy again into system. Okay, wait a second. So Q into system. So basically the energy of the system increases when you input a certain dq heat into the system and do a certain amount of work again into the system. Okay. So this is quite important, and essentially the thing is that when we have fluid flows, now one question that might come to your mind is that thermodynamics deals with equilibrium, but if you have a fluid flow, then technically they are not in equilibrium. So why are we discussing the conservation of energy and the first law of thermodynamics? Well, what happens is that at normal densities and the normal flow, viscous flows, the deviations from equilibrium are very, very small. I mean, there are exceptions to this. Exceptions can be, for example, chemically reacting flows and shock waves, for example, where there's a very rapid and sudden change of state. But other than that, in most cases, it is perfectly okay to assume that the things are very close to ordinary equilibrium. So the properties of equilibrium hold. So we can just keep on applying the law that we know about. So here, as I said, so this is the important relationship that we have to start with, which is the equation that is valid for a particular system. Now, you always have to, so by the way, the reason I specifically wrote into the system and into the system here is because in many books, the way they define heat transfer, the way we define work, that this sometimes they define it such that it is the work being done by the system onto its surroundings, so then the sign can change, right? And similarly, you have to be careful in how you are defining it. So different disciplines have different symbols, different sign conventions for these cases. Now, the other thing that I am not doing, which is in many thermodynamics books, this dq and dw, they're not written as exact differentials. In fact, there's some del is written, and they say that the d operator should only be used in the energy, and which is an exact differential, but then q and work are not, to indicate that they are path dependent processes. So we are not going to worry about that. We are just going to worry as if, or treat the entire thing as if this could be written as exact differentials. Okay. So my equation. So now basically what I have is dE by dt equal to dq by dt plus dw by dt. Okay, for a system where we remember the sign convention that this is into the system, this is also into the system. Okay, so this is my equation, the first law of thermodynamics as applied to a system. Okay, so now what we should do is, because many of you may not be extremely familiar with thermodynamics, what I want to do is I want to have a small discussion about what each of these different terms mean. So what is this energy term, what is this heat term, and what is this work term? Okay, so let us discuss these terms one by one. So first let's discuss energy. So energy is a rather weird, can be a difficult quantity to grasp, because the exact number, the exact numerical value of energy often is not that important. It is the net change of energy that is important, and it's associated with a system. It's not a physical quantity as such, and it's a number that we apply, which usually comes from formulas containing physically measurable quantities, right? So when we have energy, energy can come through different ways, and one of the chief ways where we have energy, where energy goes into a fluid system, is kinetic energy, right? Because in fluid mechanics, something is going to be flowing, so there's obviously going to be kinetic energy over there. So kinetic energy, or Ke, this particular energy is basically, it's the energy associated with the macroscopic motion of a system relative to some reference frame, and the formula for this is rather well known, and it just says it's half mv square, right? Where I just, for the time being, I just put this reference frame just to indicate that this velocity is being measured with respect to some inertial frame, right? So we have mass, we have velocity. Okay, then what is the other type of energy that fluid can hold? Well, the other type of energy is potential energy. We are probably quite familiar with this form of energy. This is the reason fluids is kept in tanks, very high up tanks which have a pretty high elevation, and then the water can just flow down to everybody's house from there. So potential energy is basically the energy associated with a system's ability to do work in an external force field, basically a conservative force field. And obviously the most common example of potential energy is when you do work in a gravitational field, right? So if you now have a body of mass m, where the gravitational acceleration is g, and it is being moved a height z, then this is the uh, this is the potential energy associated with the body, right? Z is obviously the height of the mass above some reference frame, reference plane. Okay. Apart from this two types of energy, kinetic energy and potential energy, okay, let's just be consistent. I don't have to underline this. Okay, just a second. Otherwise, later on, it will be difficult for me to. Okay, so potential energy, and then the third is internal energy. Okay, so the internal energy, or let's say IE, for a system, for a fluid, it can be composed of many different subunits. For example, it can consist of something called sensible energy. Okay, what is sensible energy? This is the energy associated with the internal molecular motion, such as the translational, rotational, the vibrational motion, and this is measured using temperature, right? So temperature is a measure of this kind of internal energy. The larger the temperature of a system, the greater its sensible energy. Okay. This is, so sensible energy is a form of internal energy. So it's sort of obvious why we call it sensible, because we can sense it through the temperature. So there is the other type of, I hope that should just immediately remind you of the other type of energy, internal energy that can be there, which is latent energy, right? So this is the energy associated with phase change, where the temperature does not change, but the phase of a material changes. For example, a solid can change into a liquid, or a liquid can change to a gas, right? Then you can also have chemical energy. Okay, I'll just keep this consistent color. So we can have chemical energy, for example, and this is the energy that is associated with the attraction of atoms, so the bond energy that is there, right? Then you can have nuclear energy, and many other types of energies can be there, and so this sort of just goes on. And nuclear energy is the energy associated with attraction between particles within an atom, such as attraction between the protons and neutrons. And there are other forms of internal energy, such as energy associated with the electric fields, magnetic dipole moments, but we don't usually encounter them, and they are not part of the usual fluid mechanics curriculum, so I'm not including them. But the entire idea is to just show that in fluid mechanics we will have these three energies, which will be quite important to us. It's going to be the kinetic energy, the potential energy, and the internal energy. Okay, so now if that is the case, then the total energy of a system, and of a system, here we are obviously implying a fluid mechanical system. The total energy E can be just written as U plus KE plus PE. It's sort of obvious what these are, but E basically is the total energy, U here is the internal energy, KE refers to the kinetic energy, and PE refers to the potential energy. And this is the equation in the extensive form. That is, the magnitude of this values depends on the mass of the system. Okay, so in terms of specific quantities, in terms of the specific quantities, E, we have the equation basically becomes E, where E, let's say, is the specific form of the total energy, and U, small u, is the specific form of the internal energy, and we have half V square plus G. Okay, just to be clear, when we are discussing, this U is not a velocity U, this is the internal energy U. I know we are using U for quite a lot of different cases, so let's just be mindful of what we are using and the context, okay, for this case. So here now V is the velocity magnitude, G is a conservative potential energy function, okay. So for our particular case, this G is basically equal to dz, okay. So this is what it is in case of a gravitational potential energy function, but this can also take up other forms depending on the conservative energy potential that is around, that is relevant in that particular case. But usually in fluids we do not encounter, I mean, in the context of our course, where we are, this is just being the introductory fluid mechanical course, we typically do not encounter the other types of potential energy functions. So the most important one is gravity, and so we can just simplify our lives and get along with it. Okay, good. So we have some handle on this quantity, okay. So basically this was the specific quantity, remember. So we basically just wrote that right now, okay, good. So we are getting somewhere here. We now have an understanding of what the specific quantity can be, and then we have also identified that the total energy E is basically a sum of the heat energy and the work and work that goes into the system. So now, before we go on into the using the Reynolds transport theorem, we should have a small discussion about this dq term and the dw term, right? Because some of you may or may not be familiar with it, so I think it's just appropriate to discuss that. Okay, so let's discuss heat Q. Okay, so this is what we want to discuss right now, and heat is basically just another form of energy interaction, where heat necessarily is a form of energy that flows between the system and its surroundings, right? And heat transfer occurs due to differences in heat in temperature. So heat moves from regions of high temperature to regions of low temperature, right? Like work, heat is not a property of the system. It is associated with a process, okay. And the amount of heat transfer during a process depends on the path taken by the process. Now, heat transfer can occur in multiple ways. There are three ways in which it can occur. One is called conduction. So conduction is a method of energy transfer where more energetic particles of a substance give energy so basically where energy flows from regions of higher temperature to lower temperature, but there is no motion involved. There is a medium involved, so you have to have a medium for heat transfer due to conduction, but the material which is transferring the heat, that does not move by itself. Obviously, one of the easiest examples to think of would be heat transfer in metals. So when you have heat transfer in metals, it's the metal which is transferring heat from one region to another, but the metal itself is not moving. Okay, so when you have heat transfer due to conduction, the rate of heat transfer q dot is given as minus Ka gradient of temperature. Okay, where this K is thermal conductivity. It's a material parameter. Vt. A is the area and T is obviously the temperature. Now you might recognize that the gradient of temperature is a vector, so this q dot actually has to be a vector. So this is a vector equation, and here the thermal conductivity is usually a scalar for isotropic and uniform materials, but this can also be a tensor in cases where you have very complex material. Okay, so K need not be a scalar, but for most materials which are nicely isotropic and uniform, you have K is a simple material property, and it's a scalar quantity as well. So this law, which is also called the Fourier's law of heat conduction, this gives you the amount of heat transfer that takes place when you have heat transfer only due to conduction and when you have a temperature gradient that is present. So obviously this minus sign is to take care of the fact that heat flows from regions of higher temperature to lower temperature. Okay, so that's conduction. Then there is another one which is called convection. Convection is just another form of heat transfer which again takes place in the presence of a medium. So it requires a medium to transfer energy from a location of higher temperature to a location of lower temperature, but in this convection the material itself moves. So you will obviously have convection when you have fluid movement. So the fluid by moving can transfer heat from one location to another. So it is a mode of heat transfer, for example, that will happen between a solid surface and an adjacent fluid surface which is in motion. Okay, and essentially it also combines in itself the conduction and transfer of energy due to advection. But in this particular case, usually for convection, if I had to calculate the rate of heat transfer, then we just calculate it as H into A again be the area of the surface, and then T surface minus T fluid. Okay. Where H is something called the heat transfer coefficient, A is again the area of the surface, and T surface is the temperature of the surface, and this is the temperature of the fluid. So this will give you the heat transfer occurring between the solid surface and the fluid. Okay. And then finally the third and the last mode of heat transfer is radiation. And radiation now takes place in the it can take place in the absence of any medium at all, and it takes place through the emission of electromagnetic waves. And in particular this case there are different laws in here, but the Stefan Boltzmann law says that the Q emitted by a body is given as epsilon sigma A, again A being this area, surface area, T to the power 4 of the whatever the material we have. So this is this Q dot again is the rate at which heat is emitted from the surface. Epsilon is a property called emissivity. Okay. And sigma is a the Stefan Boltzmann constant, its value in the SI units is of the order of 10 to the power minus 8. Okay, and A is obviously the area, once again area of the surface, and T is the temperature of the surface. Okay, with these three, so heat transfer can occur only via these three mechanisms: conduction, convection, radiation. In a given scenario, you might have all these three operative or only one may be important. Radiation is usually important only when you have very large differences of temperature, and in many cases we can often neglect radiation for small differences of temperature, and their convection and conduction become the primary mechanisms. Now, whatever mechanism of heat transfer is operative, you have to calculate all that and put it here, okay, dq. So you have to figure out what this heat transfer or how this heat transfer is taking place. Okay. We have discussed dE, right? That it is composed of the internal energy, kinetic energy, the potential energy, and then we have discussed heat transfer, that it can take place through the three different mechanisms. So we should also have a small discussion on what this dW is, although I'm sure you are quite familiar with the idea of work done. So work done W. In most cases that I have seen, the confusion with the work done arises with regards to the symbol. So confusion arises with regards to the sign of the work done. Okay, now work is an energy interaction, obviously, that is usually occurs at the boundary of a system and surroundings. Again, work is not a property of a system, but it is associated with a process that the system is undergoing, and work done on the system by its surroundings depends on the path of the process. So a quantity that is commonly often used in these contexts is power, which is the work done per unit time. But if you have to calculate work, then the differential and dW, okay, on the system, if you had to calculate that, then you would calculate that as F being the force on the system. Sorry, I'm just going to be a little economic with space, so I'll just write it niche mein. Okay, and then dot producted with ds, where this is distance over which the force acts. Okay, so this is a scalar quantity, but it is calculated as the dot product of two vectors. F is the force acting on the system and ds is the distance, right? So the net amount of work done in a given process, where if you are going to state 1 to state 2, you can write it as, let's say, where you had initial location S1 and then it is S2, then it is simply F dot ds. Okay. Okay. So now the problem with work is it can happen in many different ways, and you can have gravitational work. So for example, if you have a body, okay, so maybe I'll just draw it here. So if you have, say, a body F, a force F acting on a body, and it lifts it to through a height h, okay, then the work done on the system, okay, on the system is equal to mgh. if you have a body which is at velocity v1, and then you have a force act on it, and as a result of this force, this body it accelerates and reaches a velocity v2 after some time, then the work done on the system is, to take it from 1 to 2, is going from 1 to 2, let's say f, whatever f is, this f is on the system. Okay, I'm not going to write that, but we understand that all the time. We have to be careful as to what this f signifies. So this is the force on the system. So this is in our case, it is leading to a change in acceleration. And let's say this entire thing is happening in x direction. Okay, so then I just say I hat into, this is v dt, ds is v dt I hat, okay, going from v1 to v2. So if you evaluate this, what you will find is this comes out to be half m v2 square minus v1 square. This is just a change in kinetic energy, right, of the body. That's sort of obvious. That's what it's supposed to be. Good. Okay. Now, the most common type of work that we'd probably encounter is something called pressure work. And here is where we have to be a little bit careful, because people often make a mistake. So let's say we have a situation where we have a wall, and then we have a piston in here. Maybe I'll just draw it with a different color for the ease of it. So let's say we have a piston, okay, and here the pressure inside is P. So the force, so work done on the surroundings, it's easier to calculate the work done on the surrounding in this particular case, is the integral of the, now this F is the force on the surroundings into ds when you move from 1 to 2. Okay, so let's say you started off with x1 displacement, now you are at x2 displacement, and you have this p into this quantity will just become pa dx. Okay, these are obviously vectors, and in this particular case it's just going to move out. This moves in the x direction, right? So in this particular case, or you can write this as the pressure pdv going from v1 to v2. Okay, so this gives you the work done on the system in this particular process. Now let's always remember that work is a path dependent process, so I need to know this information about the entire path that was taken. And now that you have been able to calculate the work done on the surroundings, the work on the system is simply minus of on surroundings. So it is this quantity but with a minus sign now. So the pressure work is something that we are most likely to encounter. Okay, good. So I think what we have done is we have been able to look at all the different type of works, except over this one more thing, right? Okay, so there is something called shaft work. Okay, I'll just tell you that this comes up quite a lot, and the reason it comes up in fluid mechanics a lot is because, for example, when we have fluid going through a pump, then you can have an external moving boundary impart energy or do work on the fluid and give it energy. So in that particular case, you have to account for the work done by that. So shaft work is a very common method of transferring energy between in a fluid mechanical situation. Shaft work is most often associated with rotating fluid machines such as compressors, pumps, turbines, fans, propellers, windmills, etc. And the shaft work is usually given as the rate the time rate of change of this, or the power. Okay, so W dot is usually the torque on the system multiplied by omega. So this is again on system, and omega is the angular velocity of the shaft. So let me write it down. This is the angular velocity of the shaft, and this is the torque acting on the system. Okay, so the good thing is that now that we were discussing the conservation of energy, we started off with the first law of thermodynamics for a system. Okay, and then we said that let us look at these individual quantities and see what they are. So we looked at the energy first, and we calculated it in terms of the specific quantities right here. Then we said, okay, we just want to understand what dq means, and we saw that there are these three different mechanisms of heat transfer that are going to take place. You are going to add up all the three together to get the total heat transfer into the system. And similarly, there are many different types of work that can be done into the system, and you're going to add all of them properly and make sure that you calculate the net work into the system. Okay. So now we are ready to deal with conservation of energy for a control volume, for a CV. Okay. So to write the conservation of energy equation, we have to obviously use the Reynolds transport theorem. But we have taken the first important step, which we have figured out that the ddt of the energy of the system, okay, which is E, which is a specific quantity, dV, and this time this is the volume of the system. This quantity is Q dot into system plus W dot into system. Okay, so I'm not going to keep on writing that again and again, so we understand that. So we'll just say Q dot plus W dot. Okay, so now if we apply the Reynolds transport theorem, what do you get? You get ddt of, on this side you are going to have the integral for the control volume E rho dV. This is over the volume plus through the quantity in the through the control surface, which now beta is just E. So you have rho, then U rel dot dA. Right. This is equal to Q dot plus W dot. This is the important equation we were looking for. So conservation of energy for a CV. Okay, so and just in case you have forgotten, E, we have already written it down, U plus half V square plus G, right, where G is this conservation potential function, and you could, this quantity G is basically equal to small g into Z. Okay. Okay, good. So we have taken our first step. Now the only problem when we come to the conservation of energy is that there are so many different ways in which this heat transfer can take place in 3 ways, and this work done can occur in many different ways. But usually, so as I said before, radiation is unlikely to be an important issue in most cases, but we do have different types of work takes place on a control volume. So usually what we do is we break up this work into different constituents, and what we do is it's usual to say that the total work done on the CV, okay, on the control volume, is part of it is due to the normal forces. Okay, so the normal stresses in a fluid, what do we call the normal stresses? We call them pressure. Okay, pressure on CV plus a shaft work on CV. Okay, because it's very common to be imparting work onto a fluid body through a pump, compressor, or some of those type of things. And then W dot all others, okay, on CV. And this could be shear forces, work done due to shear forces, work done due to other mechanisms, all that. Okay, so usually we break up work into its different constituents, and one of the work processes that is rather important to us is the work done by the pressure on the control volume. Okay.